Okay, chapter 11 has to deal with permutations and combinations and the binomial theorem. So this is broken up into a few different parts. I've got quite a few examples on here, so there might be some parts of the video that you want to skip over just because I am going to be repeating some of it by showing you a few different examples. But there should be enough examples on here that you can understand what you're doing. You might need a few less, so just listen and watch accordingly. So the first thing we're looking at is the fundamental counting principle. So in here, I've got two different types of vehicles, a car and a minivan, and then you have choices. You can have a red, green, or blue of either one of those, and then you have another option to choose from, which is, do you want a 4-cylinder or a 6-cylinder? So it says, now try to list all the possible ways you could choose a vehicle. So based on those options, you have different choices that you can make, so different combinations that you can get to. Probably the easiest way to do this is by setting up a tree diagram. So if we take a look at this, if I decide I'm going to go with a car, so I can have a car, it could be red, could be a 4-cylinder or a 6-cylinder. If I went with a green car, I could choose a 4-cylinder or a 6-cylinder. If I chose the blue car, I could choose a 4 or a 6-cylinder. Or I could go with a minivan. So if I go with the van, I could choose a red one. And again, I would choose between a 4 and a 6-cylinder. I could choose a green van with a 4 or 6-cylinder. Or I could choose a blue van, and my choices or my options from there are to choose a 4 or a 6-cylinder. So if I take a look at this, I've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possible combinations of vehicles to choose from. If I break this down a little bit further, or take a look at another way, my first option was that I had to choose between a van or a car. So that was 2 choices. The next thing was my color. So I had a red, a green, or a blue, which meant I had 3 options to choose from. And then the last thing was choosing if I wanted a 4 or 6-cylinder engine. So that gave me 2 choices. So if I went and multiplied 2 times 3 times 2, I'd find that I get 12. And that's what the fundamental counting principle is based on. It's taking a look at your options and then multiplying them together to see how many possible combinations you could come up with. So the next example says, a pizza restaurant has 3 different kinds of crusts and 24 toppings. Let's determine how many pizzas we can choose that have 3 toppings. First, the number of the crusts that we can choose from. So it says we have 3 different kinds of crusts. Next, the number of toppings that we can choose from for the first topping is, well, I have 24 choices for that. My second topping, it doesn't say that I can't repeat my toppings, so I could have chose cheese as my first topping and cheese as my second topping, so that would mean I still have 24 choices. And my third topping, well, maybe I wanted a 3-cheese pizza, so I could have cheese on all 4 of those, or all 3 of my toppings, but I could have chose any of the 24 toppings as well. So that means I have 24 possible options there. So to get the total number of combinations, I would multiply my 3 choices of crusts by my 24 toppings, and my 24 topping choice to get a total of 41,472 possible pizza combinations. So I could have chose a thin crust cheese, pepperoni, and ham. I could have chose a thin crust cheese, pineapple, and mushroom, and so on and so on and so on. So altogether, to do a tree diagram with that would take you forever. So that's why we use the fundamental counting principle, which is just based on the fact that you multiply all of your possible options or choices together to see how many combinations you can make. So the next one says, a sporting goods store has a sale for a complete jogging outfit. The outfit consists of a sweatshirt available in red, green, black, or blue, sweatpants available in sweatpants available in orange, purple, pink, black, or red. Running shoes are in 8 different styles, and you have 5 different styles of socks. So it says, how many different styles of outfits can a customer choose? Well, they could choose from 4 sweatshirts. They could choose from 5 sweatpants, 1, 2, 3, 4, 5. They had, for running shoes, there were 8 different styles of those, and there were 5 different styles of socks. So if I multiply these all together, I would have a possibility of 800 different outfits. My pages seem to be out of order here. 1 second. This leads us to the following observation. I'm not sure where that page is going to be. We'll stick it in later. Fundamental counting principle states that if one item can be chosen in m different ways, and another item can be chosen in n different ways. I don't really need the word different, I just need n ways. Then the total number of choices is n times n. So that's all I did with the car and the pizza topping and the outfits, is I had m ways of choosing my shirts, m ways of choosing my sweatpants, or n ways of choosing my sweatpants. If it's only the outfit was only based on those 2 things, then I would have m times n ways. So depending on how many different things you have to choose from would be depending on how many things you're going to multiply together. So the next example says, how many different 3-digit numbers are there? So if you think about your numbers, we go from 0, when we're looking at digits, 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I'm looking at a 3-digit number, the best way to do these is to make blanks and then write in, okay, what are your number of choices for each blank? So for my first digit, I would have 9 choices. My second digit, I would have 10 choices, and my third digit, I could have 10 choices. Now you might be wondering, well, why didn't I have 10 choices for my first blank? Because I can't put a 0 there. Because then I wouldn't have a 3-digit number, I would have a 2-digit number. So that's why there's 1 less. Can't be 0. So 9 times 10 times 9, and it doesn't matter if you write this on top of it or below it. I should have written it on top of the line. But 9 times 10 times 10 gives me 900. So there would be 900 different 3-digit numbers I could make from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, as long as I can repeat. So the next one says, how many different 3-digit numbers can be formed from the digits 0, 1, 3, and 7 if we allow repeats? So it says, note, 017 is classified as a 2-digit number. So once again, that means I can't use 0 as one of my options for my first blank. So it's a 3-digit number. So for my first blank, since I can't use 0, I have 3 choices. My second blank, I can use a 0, so I have 4 choices. And same thing with my third, the 1 spot. So 3 times 4 is 12, times 4 is 48. So I can make 48 different numbers. Okay, So example 3 here says, same thing, make me a 3-digit number using only 0, 1, 3, and 7, but without repetition. So that means I can't have a number repeat. Okay, so I know for my first spot here, I can't use 0, so I can only use 3 digits in there. So then let's assume that I used 1. So that means for my second spot then, I have only 3 choices. And I've used, let's say, the 3. So for my third spot, I only have 2 choices. So I have 3 times 3 times 2, which gives me 18. So you can see by putting on a condition on there of no repetitions, that reduces my number of possible combinations. Example 4 says a true-false test has 10 questions. Suppose the answer to each question is chosen by guessing randomly. How many different sets of answers are possible? So if there's 10 questions, I have my 10 possible spots that I can fill in. If it's a true-false, then that means for every single one of these, I have 2 choices. I can choose true or I can choose false. So this is the same then as saying 2 to the power of 10, which is 1024. B part says, what is the probability that all 10 questions will be answered correctly? So there's only one right answer for both, but a possibility of 1024 combinations. So you have a 1 in 1024 probability of getting all 10 questions correct. Okay, so same thing, example 5, a multiple choice test has 10 questions with 5 possible answers for each question. Suppose that the answer to each question is chosen by guessing randomly. How many possible sets of answers are there? So if I have 10 possible questions, that means I would have 10 blanks, right? Each of these blanks, I would have 5 possible choices to choose from. So that would mean my possible different sets of answers would be 5 to the power of 10, which is 9,765,625 possible answer keys or answer solutions that I could make for this. So what is the probability that all 10 of these questions will be answered correctly? Well, again, I've got only one right answer for each one of these questions, so it is 1 out of 9,765,625. Okay, the next part of this, so we worked with the fundamental counting principle. The next piece of this has to deal with permutations involving different objects. So a permutation is just an ordered arrangement or sequence of all or part of a set. Oops, an ordered arrangement. I should put or sequence. of all or part of a set. Okay, so it's how can you arrange something? What are the possible ways you can arrange something? Either of a sequence of numbers or letters or of a set of something. So the first one says, try to list all the permutations of the letters C, D, E. Well, I could have C, D, E. I could flip my first and last letter, so I could have D, C, E. I could move my E to the middle and have D, E, C. Oops. So if I have a C, D, E, I could have a C, E, D. I don't know why it keeps switching on me here. If I had D, C, E, then I could have D, C, E, I could have D, E, C. Sorry, I got that one down there. I could have, I meant E, D, C. Or I could have E, C, D. So I have C with a D, E, I have C with an E, D. I have D in the front with C, E, and then I have D in the front with E, C, and I have E in the front with D, C, and then E in the front with C, D. So I have 6 ways to permute these, which means just 6 ways to arrange them. So a quicker way of doing this is to say that I have 3 possible ways to choose my first letter. So I could have chose C, D, or E for my first one. As soon as I've chosen one of those letters, that means in the second spot, I only have 2 ways to choose the second letter. And if I've chosen my second letter, then that means I've only got 1 way to choose the third letter. If I use the fundamental counting principle, then that means that I have 3 times 2 times 1 way of choosing, which is 6. Okay, the next example says we've gone from 3 letters to 4 letters. So it says list all the permutations of the 4 letters C, D, E, F. So I've made the list for you just to save us some time. But basically, if you look here, I went C, D, E, F, and then I went C, D, switched the F, E. And then I went C and moved my E over from this spot here. I moved it into the E spot, and then I just kept kind of doing a little rotation in there. So then I went D, C, E, F, D, C, F, E, D, E, C, F, and so on. So I just keep bouncing my letters through all of the spots, keeping D in the first spot. And then the same thing with E, and then the same thing with F. So what you notice is my number of choices for the first letter. So I could have chose 1, like C, D, E, or F for my first choice. As soon as I chose a letter for my first one, then that means that I only had 3 letters to choose for my second one. Okay, so let's say I chose D, then I've only got 2 letters to choose for my third spot, or my third letter, which leaves me with 1 letter to choose for the 4th spot. So using fundamental counting principle, if I multiplied my choices, 4 times 3 is 12, times 2 is 24, times 1 is 24. So I had 24 possible ways of arranging or permuting those letters. So what if I have 5 letters that I want to find the permutations for? Well, how many do I have? How many choices of letters do I have for my first one? I would have 5. And once I've taken one of those, then I'm down to 4, which leaves me down to 3 for the next spot. and then 2, and then 1. 5 times 4 is 20, times 3 is 60, times 2 is 120. Oops. So it says, in general, the number of permutations of n distinct objects is the product of integers from 1 to n. So factorial notation is what we're doing, or we call it n factorial. So the number of distinct permutations we have of objects is a product of the integers from 1 to n. So if we have 7 objects that we're choosing from, then our number of permutations is 7 times 6 times 5 times 4, all the way down to the number. So factorial notation is written like this, n with an exclamation mark, and that just is read as n factorial. N is just the number of objects you have, and it's solved by going n times n minus 1 times n minus 2 times n minus 3 all the way up to, and you'll have 2 times 1, and n has to be greater than or equal to 0 in order for this to work. So if it was 2 factorial, then my first, to write this out or expand it, I would have 2 times 1, so that's just 2. 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. N factorial then is n times n minus 1 times n minus 2 times n minus 3, all the way down to 3, 2, 1. Okay, so you can see here, my n for this third example was a 4, so my n it's n, 4 times n minus 1, so 4 minus 1 is 3, and then 4 minus 2 is 2, and so on. So on the previous page, we said we had 4 distinct objects. So we could say that C, D, E, and F. Okay, those are my 4 distinct objects, 4 different letters. It says we determined that there were 24 permutations, so 24 ways of arranging that, because we said in the first spot you had 4 choices, second spot you would have 3 choices, third spot you had 2, and your last spot you had 1. So 4 times 3 times 2 times 1 is just written as 4 factorial. So that equals 24. So when you have permutations involving different objects, it says you can use your calculator to determine the factorial of an integer. So 9 factorial. On your calculator, this is what you would do. You'd press the 9, then you use the math key. Okay, and the math key, if you're looking for it, is the right under on the left-hand side. You have second alpha and then math. So I do, excuse me, 9, oops, 9, then the math, and then I'm moving over to PRB, and if you use the left arrow key, it's going to move it over right over there, otherwise you have to press the right arrow key 3 times. So it's the right arrow key because we want to go to the PRB, that's the probability button. Factorial is choice 4. Okay, so it's that little exclamation mark, and then enter. So on your calculator, when you go 9, math, right arrow or left arrow key to get to PRB, number 4 to give you the factorial, hit enter. This will appear on your screen, 9 factorial, and then your answer is 362,880. So it says find the value of the following, 45 factorial divided by 43 factorial. So if you were to write this out, this would be 45 times 44 times 43 times 42 times 41 all the way down to times 1 divided by 43 times 42 times 41 times 40 all the way down to times 1. So what you notice here is because you're multiplying factors together and dividing, that you could actually cancel. So I could cancel 43 with 43, 42 with 42, 41, 40, all the way down to 1. So really what you're left with is 45 times 44. So the answer for this is 1,980. On your calculators, if you had done 45 math, right arrow, 4, enter, divided by 43 math, right arrow, 4, enter, you would get that exact same answer. So B, 24 factorial divided by 18 factorial divided by 4 factorial. So to write this out would take you forever. On your calculator, that's all you do. 24 factorial, so using your math PRB 4, enter, divide by, and I'd put a bracket in there, 18 math PRB 4, enter, 4, okay, PRB, or math PRB 4, enter, and then, or bracket, and then enter, and you'll get your answer. And you should get 4,037,880. So example 1 says, how many ways can you permute 6 different letters? So 6 different letters, you can pick whichever letters you want. It could just be A, B, C, D, E, F. It could be any combination from A to Z, but they're different letters. You're not repeating. So if I'm using 6 different letters, that means I have 6 choices, 5 choices, 4 choices, and so on. Easier way to write that is 6 factorial. Use your calculator, and you find that your answer is 720. How many ways can you permute the letters in the word factory? So we've got 1, 2, 3, 4, 5, 6, 7 letters. None of them are repeating, so I have 7 distinct letters there, 7 different letters, so it would be 7 factorial, so 5,040. How many ways can 5 people finish a race if there are no ties? So that means that you can't have 2 people in first place or 2 people in third place. So that means I would have 5 choices for first, 4 choices for second, so on, 3, 2, 1. So that is the same as 5 factorial. So your answer is 120. Okay, the next one says, let's consider the letters A, B, C, D, E. Suppose we want to arrange only 2 of these letters. How many ways could we do it? So if we draw this out, for our first choice, we would have A, B, C, D, or E. So our second choice then, if I chose A as my first choice, then I could have AB, or I could have AC, AD or AE. If I had chosen B, then I could have BA, BC, BD, and BE. With a C, I could have CA, CB, CD, CE. And then for D, oops, I kind of did two in a row there, so I could have DA, DB, DC, DE. And then E would be EA, oops, EB, EC, and ED, because I can't have any repeats. So in total then, if A was my first choice, I would have 4 choices. If B was my first choice, I'd have 4 arrangements. C, 4, D, 4, and E, 4. So a total of 20 choices. To do that mathematically, I would have 5 choices for my first letter. For my second letter, I would have 4 choices, because I can't choose the same letter that I chose for the first spot. So that would be 20 choices. So this would be using the fundamental counting principle. I should have wrote that under there. So as a diagram, that's the way it would look like. My first choice, I have A, B, C, D, E, so I'd have 1 letter for each. And then to expand it then, if I chose A, then I'd have all the combinations A, B, A, C, A, D. So using the fundamental counting principle, I had 5 choices of letters for my first letter, and then 4 choices of letter for my second. If you did this, or we could use factorial notation to calculate this. So what happened here is I had 5 times 4 times 3 times 2 times 1. But I was only left with a 5 times 4. So that means that I would have had to divided by 3 times 2 times 1. Because these then would have canceled each other. So really, if I write this out on the top, I would have had 5 times 4 times 3 times 2 times 1, which is 5 factorial, over 3 times 2 times 1 is 3 factorial. So what you notice is I have all my possible choices divided by the choices that I don't use or that I can't use. So it says, in how many different ways can we arrange 3 of the 5 letters? So I've got 5 possible ways of choosing it, but I'm not going to use all of them. I'm only using 3 of them. So then that leaves me with 2 factorial ways that I'm not choosing, or combinations I can't use because of repeat. So 5 factorial divided by 2 factorial would be 5 times 4 times 3 times 2 times 1 divided by 2 times 1. So that's just 5 times 4 times 3, which is 60. So in general then, the number of distinct objects taken r at a time is given by n factorial, so the total number of arrangements you have, so permutations or arrangements you have of the objects, but how many are you taking at a time? So n, if r is how many you're taking at a time, then you divide it by how many are left. So it says underneath there, we often represent this as NPR or n permute r. So n permute r looks exactly like this. N permute r is equal to n factorial over n minus r factorial. So if I have 8p3, using my NPR formula, that would mean this is my n value, this is my R value. So I would have 8 factorial over 8 minus 3 factorial. So that's the same as 8 factorial over 5 factorial. So if you were writing that out, that would be 8 times 7 times 6, because your 5 times 4 times 3 times 2 times 1 would have canceled out with the bottom. So that equals 336. So you could, on your calculators, do 8 factorial using that 8 math, right arrow, 4, enter, divide by 5, and all that. Or you could actually use the permutation key. So on your calculators, it's using that math button again. So I would enter 8 so 8 math. Whoops, I got a little small there. So 8 math. Use that left arrow again so that I go into PRB. Followed by, if you look, your second choice on there is NPR. So that's choice 2, which gives you the permutation formula. And then you enter in what your R value is. So in this case, my R value is a 3, and then enter. And you get 336. So the permutation function on your calculator makes it a lot easier when you're doing a question where you have restrictions on it. So take, for example, on one of the pages before when we had that 5 factorial over, what was it, 5 over what? Or sorry, 24 factorial. Oh, I'm looking at the wrong one. 45 factorial over 43 factorial. So if we had instead written it as 45 over, or 45, and then your R would have been a 2, because the difference between 45 and 43 is 2. Okay, next example. Whoops. How many 4-letter permutations can you form with the letters in the word factory? So the last time we did this is how many ways can we arrange the word factory. Now it's saying I want to take these 4 at a time. So my R then is 4. My N is equal to how many possible combinations do I have there, or not combinations, how many possible arrangements do I have there? So I have 7 letters I can arrange. So that means that for permutations, this would be using my NPR. I'm taking 7 distinct objects and I'm permuting them or arranging them 4 at a time. So using my formula, it's 7 factorial over n minus r, so 7 minus 4 factorial. So 7 factorial over 3 factorial. So if I were to write this out, it would be 7 times 6 times 5 times 4, because my 3, 2, and 1 would have canceled out with my bottom. And then I never did write my answer in here, so what is it? 840. Okay, that's a lot of work, so just use your calculators to do your 7 math, 2 for NPR, 4 enter, and you would get that answer. So it says 5 people are in a race. How many ways can gold, silver, and bronze medal be awarded to 3 of them? So I've got 5 people, and I'm choosing 3 at a time, or 3 distinct arrangements at a time. So this would be, my N then is 5. That's my total number I can choose from. I'm arranging them 3 at a time. So this would be 5 P3 writing it out would be 5 factorial over 5 minus 3 factorial. You use your calculators, either using the NPR button or writing down 5 factorial divided by 2 factorial. Your answer is 60. Okay, so it says so far you've learned how many permutations there are of 7 objects taken 4 at a time. So using our NPR, this would be 7p4, and when we calculated that, up on the top there, it worked out to be 840 possible ways of arranging those. So it says how many ways can you permute 7 objects taken 10 at a time. So for 7 permute 10, that would look like 7p10. And if you did this, writing it out, you'd have 7 factorial over 7 minus 10 factorial, which would equal 7 factorial over negative 3 factorial. Now in your calculators, if you tried to do negative 3 factorial, you'll get an error because you can't do the factorial of negative values. Okay, can't do the factorial of negative numbers. And if you think about this logically, if you have 7 objects, how can you take 10 at a time and arrange them? You can't. You're 3 short. So the next one says, okay, then let's look at a 7 permute. So if I did a 7 permute 7, so let's take 7 objects, 7 at a time, this would be 7 factorial over 7 minus 7 factorial, which is just 7 factorial over 0 factorial, which is equal to 7 factorial. So if you put that in your calculator, I can't remember what exactly your answer is, but what you find is 0 factorial. So if you take 0 objects and arrange them, you have only one way of doing it. If you take nothing, there's one way to arrange nothing. So 0 factorial, kind of like any number to the power of 0, always equals 1. So it says, in general, there are 3 restrictions of n permute r. So if we have n permute r or NPR, which is expanded as n factorial over n minus r factorial. So you can do this if your n is greater than or equal to 0, your n has to be greater than or equal to r. So I can't take 7 objects and arrange them 10 at a time. And your r has to be greater than or equal to 0. Because you can't say I'm taking 7 objects, arrange them in negative 7 ways. That doesn't work. You have to arrange them at least in either 0 ways or in 1 way. So it says, example 6, use the formula, the n permute r formula, to determine which expressions are defined or not. So if I look at the first one, 4p7, well, right away, n is less than r, or r is greater than n, so this one would be not defined. 8p5, so my n is greater than r, so this one would be defined. So what that means is you can calculate it. 7p0. So this is, whoops, n is greater than r. So this would be defined. And this one, if I did it using my formula, I would have 7 factorial over 7 minus 0 factorial. So it'd just be 7 factorial over 7 factorial, which is 1. So everything would cancel off and leave you with 1. Next one was negative 8p5. So one of my stipulations was that n had to be greater than or equal to 0. Well, in this case, n is less than 0, so this one is not defined. The last one was p5 or p permute 5. So no, my p, let me try that again. My n is equal to my r, which is okay because it can be greater than or equal to r, so this is defined. If I expand this, this would be 5 factorial over 5 minus 5 factorial, so that's like the 7 one we did before, which is the same as 5 factorial. Because 5 minus 5 is 0, 0 factorial is 1. Okay, and the last one on this page says, suppose we want to write NP3 without using factorial or NPR notation. So I don't know what my n value is. So NP3 would mean I would have n factorial over n minus 3 factorial. Well, n factorial, what we want to do then, to write this out, without having it in factorial or the permutation notation, what we need to do is get rid of the denominator. In order to do that, we have to expand it first. So n factorial, from our definition near the beginning of this lesson, n factorial is the same as saying n factorial times, not n factorial, n times n minus 1 so n times n minus 1 times n minus 2 times n minus 3 times n minus 4. And I could keep going, but actually I'm just going to go to that n minus 3. On the bottom then, if I leave this as n minus 3 factorial, where I've ended on the top there at n minus 3, I could keep going past that. So it could be like, if I forget about the stuff at the beginning, it could be like having n minus 3 factorial, because then I would be going n minus 3 factorial, n minus 4 factorial, n minus 5 factorial, and so on, which is the same as the bottom here. N minus 3 factorial is going to be n minus 3 factorial minus n minus 2, or n minus 4 factorial, n minus 5, and so on and so on and so on. So really, this will cancel out this. So what I'm left with is n times n minus 1 times n minus 2. So that's how I can write out NP3. It's n times n minus 1 times n minus 2. So what you notice, it's everything in between n and the 3. So I would start with n, then n minus 1, n minus 2, n minus 3 will cancel out on the top and the bottom. Okay, the next one says we're going to take NP4 and expand it, same way as we did in the other example here, without writing it, just leaving it either in factorial or in the permutation formula. So NP4 means that on the top, excuse me, I got tickled. On the top here, I would have n factorial. On the bottom, I would have n minus 4 factorial, or n minus r factorial. So if I expand my top, this would be n times n minus 1 times n minus 2 times n minus 3 times n minus 4. Now I'm going to stop there because then it's identical to my bottom. So those two cancel, so I'm left with this is equal to n times n minus 1 times n minus 2 times n minus 3. So n plus 3 factorial divided by n minus 1 factorial. So if I expand my top, this is n plus 3 times n plus 2 times n plus 1 times n minus 1. And it could go on, but I'm going to stop there because now that is identical to my bottom of n minus 1 factorial. Those cancel. So my answer is n plus 3 times n plus 2 times n plus 1 times n. So example 8 says solve for the unknown variable. So I'm working backwards kind of. So 1680 is equal to 8 factorial over 8 minus r factorial. So I want to get my unknown, my 8 minus r factorial, by itself. So that means that I'm going to switch this around. I'm going to cross multiply and move these. So I would have 8 minus r factorial is equal to 8 factorial divided by 1,680. So 8 minus r factorial is equal to 8 factorial expanded would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 1,680. So if I were to multiply on the top, 8 times 7 input equals, times it by 6 equals, times it by 5, I'd see that by the time I got to the 5, that those numbers multiplied together would equal 1680. So my 8 times 7 times 6 times 5 would cancel with my 1680, which leaves me with 4 factorial on this side. So 8 minus r factorial equals 4 factorial. So by my fancy math, factorial and factorial would just cancel each other. I could divide, if I divide this side by the left side by factorial, I divide the right side by factorial. So I'm left with 8 minus r is equal to 4. If I bring over my 4 and bring over my r, 4 is equal to r. And you could check it then. You could go 8p4 on your calculators and you'll get your answer to be 1680. So let's try it for the next one. NP3 is equal to 120. So what this is saying is, whoops, I don't want to put an equal sign there. 120 is equal to n factorial over n minus 3 factorial. So if I expand my top, I would have 120 is equal to n times n minus 1 times n minus 2 times n minus 3, and I'm going to stop there because now that matches my bottom, or my denominator. Those two will cancel. So I have 120 is equal to n times n minus 1 times n minus 2. So if I multiply what is left here, so this is what I'm left with. If I multiply that out, I have 120 is equal to n times n minus 1 times n minus 2 is equal to n squared minus 3n plus 2. Multiply that n through. I have 120 is equal to n cubed minus 3n squared plus 2n. So to solve this, I need to have everything over to one side and my equation equal to 0. So I'd have 0 is equal to n cubed plus, whoops, not plus, minus 3n squared I better erase that so it doesn't get confusing. N squared, oh my goodness, minus 3n squared plus 2n minus 120. Now you could factor that if you had all of the steps and lots of time, but instead what you would do is you'd put this into your graphing calculator. And when you're doing your trace then, we want to find, oops, trace, we want to do the 0 function. We want to find the zeros of that graph. So when you do that, you'll find that n is equal to 6. So this graph would cross the x-axis at 6. Okay, the last one, n plus 2 factorial is equal to, or over n factorial is equal to 56. So this one, they've already got it to this step right here. So what we're going to do then is just expand it so we can cancel our denominator. So this is n plus 2 factorial, or not factorial, I always want to throw that in there, just n plus 2 n plus 2 times n plus 1 times n. Okay, now I'm at my denominator, so I put my factorial in, leave it there. N factorial is equal to 56. So I cancel, I have n plus 2 times n plus 1. So if I multiply those together, that leaves me with n squared, excuse me, plus 3n plus 2 is equal to 56. So I'll just bring this over here and finish solving it. I bring my 56 over, so it'd be a minus 56. So n squared plus 3n minus 54 is equal to 0. Product and sum means that I would have n plus 9 times n minus 6 equal to 0. So n is equal to negative 9, or n is equal to 6. Now according to my 3 rules, or my 3 restrictions on here, my n can't be a negative, so my answer is n is equal to 6. Okay, I'm actually, for this part of the lesson, I'm going to pause here, and then I will continue on. No, actually, I'm going to finish this one. I'll do this all in one shot. It's going to be a little bit longer, but it'll get you through the whole section. And again, like I said, there's lots of examples on here, so you might want to jump over a few of these. Okay, this is where I've got a page out of order. That's why this isn't making sense. So I'm going to go near the top. This page here, I think. There we go. So I'll just jump back to the next page. So permutations involving identical or different objects. So in the previous part that we were working on, we listed all the permutations of A, B, C, D. So we had n distinct objects, the number of permutations we had then. So when we took these however many objects and we arranged them, we had n factorial ways of arranging them. So remember, for this one, we had 4 factorial ways. We had 4 letters, 4 ways to arrange them, because the first choice we had 4, then it was 3, then 2, then 1. So 4 times 3 times 2 times 1 is the same as 4 factorial, so we had 24 permutations. So that's what we did in the last section there. So it says, but what happens if we change B in the given list of objects into an A? So we would have a second A in there. So instead of having in all of these spots where we had B's before in that original list, we're going to have A's. Okay, so I went from having ABCD to AACD, ABDC to AADC. So you can see all I've done is wherever I had a B, I had an A. So if I look at my unique sets here, well, this first set here, AACD, was the same as this one. Then I had an AADC, and I had an AADC here. ACAD, ACAD. I had ACDA, ACDA. I have to pull up my rainbow here. ADAC, ADAC. CAAD. And CAAD are right there. CADA, so CADA and CADA. CDAA. Where did CDAA go? Am I missing one here? Oh, I have to add a set, sorry. I'll do that one in a minute. So DAAC and DAAC. DACA and DACA, and then CDAA. And I need to add an extra one here because I missed a row. DDBC, yep, this one here. I'll write my black in. So this one here, I must have just cut it off. This one should have been ADC blank, and then this would have been blank DCA. This one was CD blank A, and this one was DC blank A. So this one should have been an A, and A. So it just got cut off there. Sorry about that. So ADCA and ADCA. It's kind of hard to see that color. I better choose a darker one. CDAA, CDAA. And then my last one, here, let me pick this yellowy one. DCAA and DCAA. Well, that's exactly the same as that one. I better change that color to a, let's go with a gray. Kind of the same as that one. Well, we'll pretend it's different. Here. Okay, so if I look at my distinct objects here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 unique sets. Because I repeated a letter, I was left with 12 unique sets. So it says try to, the next one, determine how many unique permutations there would be if we additionally change the C into an A. So not only would our B's be A's, but our C's would be A's. So we'd have 3 A's in each one So AAAs. Okay, and if I looked for unique sets, so triple AD, all of these. AADAs, all of those. Triple AD, well, that was the same as this one. Triple AD, triple AD. AADA was the same as my red one, so that wasn't unique. ADAA. So ADAA, 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 that's ADAA, that's ADAA, and that's ADAA. DAAA, DAAA. So all of these, this whole column here, are all D triple A's. Haven't used green. So how many distinct or unique sets do I have? Well, there's 1, 2, 3, 4. So you'll notice when I had 4 different letters and I arranged them, I had 24 possible arrangements. When I only had 3 choices of letters but 4 spots to fill, I went down to 12 unique sets or 12 unique arrangements. When I repeated one letter 3 times but still had 4 spots to fill, I only had 4 unique arrangements. Oh, now I have to go back down to my last page, or my pages here. So, when I had a triple AD, that's the way. It says for each permutation ABCD, you can hold the D in one place and rearrange ABC. Okay, so when I kept the D in the same place, like these couple of spots here where I've got the dots, I had a choice of ABCD. I had a choice of ACBD. I had BCAD, BACD, CBA, and CAB. So when D has a restriction on it, what do you find out? So when I say D has to be in one particular spot, and it wouldn't have mattered if I'd said it was the first, second, third, or fourth spot. I just chose the fourth spot for this example. But when I say that D has to be in a particular location, that restricts my number of arrangements or unique sets that I have. So I have 6 permutations only this time. Six permutations when D has a restriction. Or, not 6 factorial, or if I think of that, I have 3 factorial ways of arranging that. So when we changed BC to A, okay, so we left the letter D, changed our BC to A's, what we found then is that 6 of our permutations were exactly the same. So we had AAAD, 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 AAAD. So 6 of the permutations that we had before were exactly the same. And we counted each unique one as a set. Okay, so each unique one was a set. So we had a set of AAADs, and there were 6 in that set. So we counted it basically 3 factorial times. Okay, we said there's 6 different ways of doing that. So to find the correct number of permutations, when we have these restrictions, we divide the total number of permutations which was 4 factorial because we had 4 spots, so 4 different ways of arranging them, by the number of identical permutations. So we had 3 identical permutations in this example. Or, if you want to think of it another way, is by the number of repeats. So in this case, we had 3 factorial, or 3 ways of repeating that. So if I take a look at this one, my total number of ways when I didn't have any restrictions on there, I had A, B, C, D, and I was 4 different letters, or 4 spots. I had 4 factorial ways of arranging them. When I said that 3 of the letters were A's and 1 was a D, then that cut down my number of possible unique arrangements. So what I did is I divided it by those repeats. So this is 4 times 3 times 2 times 1 over 3 times 2 times 1, which is just 4. Okay, I'm going to pause there for this one, and I'll finish the next one in next ones of these examples in another recording, just so that it's not so long and for you to download this one.